In this video, we're going to go through the process of conducting a hypothesis test for the mean with sigma unknown. So we talked in the previous video about the process of and kind of the idea behind a hypothesis test, the fact that we're going to have to set up what we call our null and alternate hypotheses and kind of conduct the entire thing like a criminal trial. There's going to be two approaches to a hypothesis test, and we're going to cover both of them here. So there's two different methods. So there are two methods. To conduct one of these tests. Okay, so I'm going to give us a setup, and we're just going to go through this using an example. So here's the example that we're going to look at today. Talking about exam scores. In this case, the ACT, which is like a college entrance type exam. The average ACT score is 20.8. The score is, I think, on a scale where it's up to 36. I think 36 is the highest score you can get. So the average ACT score is 20.8 with a standard deviation of 4.8. And there's a company that's like a test prep company, so an ACT test prep company that tutors students. They claim that students coached by them have a higher average score. So they claim that students that they tutor have a higher average score. And as evidence of this, so as evidence, they have a simple random sample of 80 students, and the average score of those 80 students that have been tutored by them is like a higher number. 22.3 is what we're going to use. So as evidence, a simple random sample of 80 of their students has an average score of 22.3. Can we conclude that their tutoring is effective? So can we conclude that their students score higher at what we're going to call a significance level? And I'll come back to what this means, but at a significance level of 0.05. Okay, so just the setup of this problem takes forever, just writing the problem down. Luckily, the problems you're going to be dealing with on the homework and on any future exams will already be written down, so you won't have to go through this. But this is the idea. We know what the, let me get my pointer here. We know what the average ACT score is of all students. It's 20.8, and here's the standard deviation of all of those students. Oh, and you know what? I have a typo up here. I'm not going to go back and redo all of this. This is supposed to be where sigma is known, because right here I'm telling you what sigma is, so it's definitely known in this case. Okay, so this should have not have said unknown, it should have said known. So in this case, the standard deviation is 4.8, the mean is 20.8. This is of all students that take the ACT. The ACT prep company has students that they claim score higher, and as evidence they point to a random sample of 80 of their students whose average score was 22.3, which is clearly higher than 20.8. And the question is, we have some evidence that shows that yes, their students do better than average, but this was only 80 of their students. Maybe they have thousands and thousands of students. How do we know that they didn't just get lucky in the sample that they took, and that this 22.3 was just a fluke, a product of happening to get lucky when they picked their 80 students? So this is really what the question boils down to. This is the idea behind a hypothesis test. We'll have something that we're trying to test, something that evidence is supporting. It looks like their students score higher on average, but we want to know, is it just a total fluke? And so here's the idea. The first approach, so we had these two methods. The first approach is going to be called the critical method approach. And I'll talk about that here. Sorry, the critical value method. There we go. Okay, so again, the question is, yes, 22.3 is higher than the 20.8. But could this just be a fluke? Well, the answer is yes, it could be a fluke, and really the question is, how likely was it to be a fluke? If it's a very slim chance that this was a total fluke, then we'll be pretty confident that, yeah, this is indeed their students do score better. This number's higher than this number because their students score better than the average student. But it's also possible that maybe we find out there's like a 50-50 shot that this was a fluke. And in that case, it's not very convincing evidence that, that their testing service improves scores. So that's going to be kind of what we're looking at. Okay, so the process to figure all of this out is, I'm going to kind of outline it here. Let me draw a picture, because this is the easiest thing to assume. We start off all of these tests by assuming that the null hypothesis is true. So we need to set up our null hypothesis. We saw this last time. This is always the initial assumption. So what are our null? So we want to state our null and alternate hypothesis. So let's do that right here. This is something that we should have gotten a little practice with in the last section. So here's my null hypothesis and alternate hypothesis. We've got to decide what they are. The null hypothesis, again, is that the answer to the question that's asked is no, that their testing service doesn't do anything. It doesn't help at all. And if their testing service doesn't do anything, then the average score of their students should be the same as the average score of everybody. It should just be, Jesus, the pen is not working right now. Average score should be the same 20.8 as everybody else. But the alternative hypothesis, the alternate hypothesis, is no, that their test prep did improve scores, and so that their scores, mu, the average score, so what we're saying is mu is the average score of all the students at the test prep company. The null hypothesis is no, it makes no difference to take their test prep or not, and the average score of these students at the test prep is really the same as everybody else. And the alternate hypothesis is no, it actually is effective. Their average score is higher than the 20.8. So this follows the same rules that we talked about, where this has to be an equal sign and these numbers have to be the same number. This is our form. And what we wind up with is what we call a right-tailed alternate hypothesis. Okay, so we've started by assuming that this is true. This is going to be our default idea, that really the average score of all these students is the exact same 20.8 as everybody else. And if that's true, then I'm going to take a look at the sampling distribution. So here's the picture of all the possible values that we could get in taking a sample from this group. So here's my sampling distribution. Again, that's what we've got here. I'm going to write this up here, sampling distribution. This is the distribution of all the possible x-bar values that we've got. And under the assumption that the null hypothesis is true, the average score is 20.8. So we're assuming this is true. And by assuming this is true, that the mean score of all students at the test prep company, that value of mu is 20.8, that puts it at the center of our sampling distribution. And the evidence that we got is this 22.3. So we took a sample, we didn't, the test prep company took a sample of 80 students, and they found for their 80 students that their x-bar value was 22.3. There we go. And we want to know where this falls. Does it fall over here? Does it fall over here? Does it fall over here? We don't know exactly where this 22.3 falls. If it falls in one of these regions, say right here, then it's not all that far away from this number. It doesn't look like that would be all that uncommon of a result. So the idea is they took a sample and they got their x-bar was 22.3. If it falls close to this number, well, that's what happens most of the time. 22.3, maybe it's really close to this, and you need a much bigger number to be over here on the tail. And maybe it's possible that if they took a different sample of 80 different students, they would have wound up with an x-bar over here below 20.8. Maybe they would have wound up with one like 19 or something like that. So the question is, where does this result fall? If it falls over in this region, so if it falls here, if this is where that cutoff is, that's not a very weird result, right? It's pretty close to the result that I was expecting, 20.8. But if it falls over here, or even further way over here, now we're getting into a region where that would be considered a weird result. So again, this is the tricky part, what we've got to keep in mind. We're assuming that the students at this test prep company don't really score any better or any worse than anybody else. And we want to look at this result and see, under that assumption, under the assumption that they don't score better than anybody else, is this a weird result or is it a not weird result? If it's close to the value I was expecting, it's not that weird. If it's way out here in the tail, that would be weird. That would be unlikely to have just totally happened by chance. And that's what this ultimately boils down to. So we just need to figure out where our x-bar falls. And to do that, we need to compute what's called the test statistic. So to determine where x bar winds up, we need to compute its z-score. Which is called the test statistic. Put that in parentheses there. And so that test statistic looks like this. We compute the z-score, we take the value that we just found, it was x bar, we subtract off the mean, which was the 20.8, so this is going to be actually mu 0, we'll put that 20.8 there, and we divide by the standard deviation, which for this thing is the standard error, sigma over the square root of n. So here is our formula for this thing. When we actually plug in the numbers, x bar, that's the 22.3, I'm subtracting off the average, which was 20.8, and then I divide by sigma over the square root of n. Well, sigma was given in the problem, somewhere up here. Right, the standard deviation, right here, 4.8. And the sample size was 80, so there's my sigma and my n. So let's go back down to here. My sigma was 4.8, and I'm dividing that by the square root of 80. And if we're plugging this into the calculator, maybe toss some parentheses around the numerator, toss some parentheses around the denominator, make it a little easier on ourselves. And let's plug these into the calculator. And I will get, let's see here, I get about 2.80. 2.80. Okay, so now I can actually locate this on the graph. I'm going to redraw our graph here. Here's all the possible x bars. The center of this graph by assumption is 20.8. And ballparking where these standard deviations occur, maybe there-ish, there-ish, there-ish. We just found that this one had a z-score of 2.8. It's way over here. Right? If this is z equals 1, 2, 3, and so on, here is right there. Oops. Right there is z equals 2.80. So to me, that looks like it's going to be a weird result. It's really far from the area where we'd expect most of the results. Most of the x bars fall over here, and this x bar fell way over here in the tail. So the question is this weird? Is this a weird result? Well, we need to quantify what we mean when we say weird. And this is where that idea of the significance level that I mentioned at the beginning of the video comes into play. So when we framed this question, I said we're using a significance level of 0.05. The significance level is basically where we're going to define what we consider weird. So is this a weird result? Zoom in here. There we go. The significance level is 0.05, which is the probability we consider weird. Or unusual. And we've talked about this in the past. 0.05 has often been the cutoff for what we called an unlikely event. In this case, that significance level, we're going to use a letter you've seen before. It's that alpha equals 0.05. So this region, this is the probability that we're going to define as weird. If I changed it to alpha being 0.01, what we'd be saying is I'm going to consider something weird if it happens less than 1% of the time. In this case, I'm considering something weird if it happens less than 5% of the time. And so we need to figure out where that region is, where that occurs. And in this particular case, we're going to be able to find this value using our table that we had before. So what I'm going to do is basically say, I'm going to draw this region that I consider weird, and it's going to be this region right here. This is the region that we consider weird. Here's where alpha equals 0.05. The reason that I'm drawing it all on the right side is because we had a right-tailed alternate hypothesis. This is the side, the region where all our calculations are going to concern, where they're all going to happen. All of our calculations are going to be calculated in that right tail. We call this region the critical region. And it's the region defined by the significance level. Right? That is our significance level. So it tells us what are we going to consider weird. In this case, I'm going to consider the top 5% of values weird. And looking at it, to decide whether our result falls into this region or not, clearly the way I've drawn it, it does. But to know for sure, I would want to know what that number is right there. What is that z-score? If our z-score winds up being a bigger number than whatever the z-score is right here, then I'll know that we're in that weird region. And this cutoff right there is going to look familiar. That's going to be what we call the critical value. And that's why this is called the critical value method. So what is the z-score associated with this top 5% of the area? So that critical region, basically what we're saying is right here, I'm going to put a divider. Any result that falls over here, we're going to say that's not weird. Any result that follows over here or falls over here, that's going to be considered weird. The critical region is just the weird region. Any results that fall on this side, they're close enough to the value I was expecting that I'm going to consider it to not be a weird result. But if it occurs on this side over here, then I'll consider it weird. It's far enough away that I consider it weird. And so if I can find this number, that'll be how we define weird. And if this number, our test statistic, winds up being bigger than this number, the critical value, it'll be a weird result. So let's check out and see if we can find that number. So what is this value? It's called the critical value. And it's exactly the same as the critical value that we used when we were doing our confidence intervals. In this case, I should erase this. Let me come back up here and edit this a little bit. I cheated a little bit. So let me erase this. That's not actually going to be quite what this winds up looking like. I'm actually going to call this, instead of z sub alpha over 2, I'm going to call it z sub alpha. Okay, it's called the critical value. And the notation we're going to use for it in this case is z sub alpha. So let me go into this notation. So let me do a quick side note. Let me sneak it over here. Let's do it on the side. So this is sort of a quick aside. I'm going to box this off from the rest. In this case, we're calling this z sub alpha, and that's because, looking at our picture, it's the z-score associated with an area of alpha in the right tail. So here's alpha equals 0.05. All 5% of that area is all in the right tail. So this z-score is associated with just that 0.05. But this was a right-tailed hypothesis. It's possible to have one of the two other forms that we've talked about. It could have been a left-tailed or a two-tailed hypothesis. If it was left-tailed, this would be the region that we would be considering weird, over in the left tail. And instead of using z sub alpha, it would be the same z-score to cut off this mirror image region, except for we've talked about it before. If this z-score is some positive number, the mirror image z-score will be the negative of that same number. So if we have a right-tailed hypothesis, as we do here, this is the notation we'll use. And it's because all of that area alpha is all in the right tail. If it was left-tailed, we would use the same number, but it would be the negative of the z-score. So this would be in the left-tailed case. But if we had a two-tailed alternate hypothesis, it's possible that our regions we consider weird could show up on either side. And so I would have to split this 5%, my significance level. The most extreme 5% is what I'm going to consider weird. If it's right-tailed, all of that area is over here. If it's left-tailed, all that area is over here. If it's two-tailed, that area is split 50-50. Half would be over here, half would be over here. So instead of using an area of alpha, I would need to use an area of alpha over 2. And we would write z sub alpha over 2. This is the case where it's two-tailed. And this is the notation that we used before for our confidence intervals. And it's because, if you remember our pictures in our confidence intervals, we were always looking at a picture where we were interested in cutting off both of those two regions. Maybe we had 95% of the middle region, and we had the remaining area in the tail. That's what we're calling alpha. Sorry, alpha. Ooh, let's redo that. That's what we're calling alpha. But half of it's over here, and the other half of it is over here on this side. And that's why we had to use alpha over 2. So I'm going to erase this, but you'll notice it's the same idea as we did with confidence intervals. And this hopefully explains why we use that notation. Alpha is supposed to be the amount of area in the tail. And so, or really the total amount of area in possibly both tails. And that means in this case it would be half of it over here and half of it over here if it was two-tailed. So that's the idea. This notation, we'll use 3 different notations for our critical value. We'll use the familiar notation whenever we have a two-tailed hypothesis, and we'll just use alpha all by itself if we're in the right tail or the left tail exclusively and not both tails. So again, alpha, if all the area is in one place, alpha is that area. Alpha over 2 if that area is split between the two tails. Okay, so how do we find it? Well, we've done this before. I'm looking for, in this case, the amount, I want the z-score, z sub alpha. So what is z sub alpha in this case? It is the z-score associated with an area of 0.05 in the right tail. And we can use table A3 to find this value. So I'm going to go over here to the tables, which I've pasted onto the side here, and this should be table A3, sure enough. So when we were doing confidence intervals, we used this label down at the bottom of the table. But now that we're doing hypothesis tests, we're going to use this label up at the top, the amount of area in the right tail. That's exactly what we're looking for in our picture. So let me center this so we can see both. Right, we want this area over here in the right tail. How much area is in the right tail? 0.05. Looking at this, how much area is in the right tail? 0.05. So this is the column that I'm interested in, and we'll use this the same way we did before. If we're dealing with a t-distribution, we'll use the degrees of freedom in the same way that we did previously. But if we're dealing with a normal distribution like we are here, I'm going to use this row. So 0.05 down to the bottom. Here's the z-score associated with that. Z-score is 1.645. This number, so basically I'm using that, and I'm using that to give us the number that we're looking for. Notice it's associated with a confidence level of 90%, because if we had a confidence level of 90%, where 90% is in the middle, that would leave 10% total for the tails, which would be 0.05 on this tail, 0.05 on that tail. So let me erase that quick little sketch, but that's kind of the idea. So this is how we're going to use the table. We're now using the top label on the table to figure these values out. So 1.645, that's my number. Sorry, let's get this again. 1.645. And again, this is our cutoff for what we're going to consider weird. It defines the edge of the shaded region up here, and that's the region that we consider weird. So did our result, the z equals 2.8, fall in that weird region? Absolutely. So is z equals 2.80 weird? Yes, definitely, because it's more extreme than the cutoff we had for weird. Anything bigger than this is going to be considered weird. This is definitely bigger than this. So that is the critical value method. In the critical value method, we compared these two z-scores. To decide if our result, which in this case was our result, what I'm talking about is getting an x-bar value equal to 22.3, is that weird, under the assumption that the true average should only be 20.8. And in this case, we said yes. So we just got a weird result. Finding x bar equals 22.3 is weird. If, as we claimed, mu was equal to 20.8. So if the true average is 20.8, it's weird in our sample to get an average of 22.3. But this goes back to the assumption we made. We assumed that this was true. And if making the assumption that this is true leads to a weird result, what does it tell us about that assumption? Maybe assuming mu equals 20.8 is a bad assumption. If we make an assumption and we start getting weird results from making that assumption, maybe it's not a good assumption. And if it's a bad assumption, what should we do to it? So going back up here, we assumed this was true. We just got weird results assuming this was true. It led to very weird results. So maybe it was a bad assumption. What's maybe a better assumption? Well, our alternate hypothesis. Maybe it's a better assumption that mu equals 20.8. Mu is greater than 20.8, that it's a larger value. Essentially what I'm saying is drawing our picture again. One last time. We're going to draw this picture a million times. Here is mu equals 20.8, and our result was way over here. Here was our x bar equals 22.3. This is a weird result. But it's only weird under the assumption that this is the curve that we're dealing with. Sorry, let's click that. It's weird under the assumption that this is the curve that we're dealing with. Apologize. Okay. If instead our curve is actually over here, if this is where our curve is, now it's not such a weird result on that one, so it's not weird. It's weird for the black one, so it's not weird for the red one. It is weird for the black curve. This result is only weird depending on context. In this case, we assumed mu was 20.8 and it led to a weird result way over here in the tail. But if we instead assume this red one is the correct distribution, well then we're right near the middle and it's not weird. But if we assume the red one is true, then what do we know about the value of mu? I don't know exactly what it is, but how does it compare to this 20.8? Well, it's definitely further to the right, meaning it's definitely greater than 20.8. So we get a weird result assuming that mu equals 20.8, and maybe we get a not weird result if we assume that mu is in fact greater than 20.8, and we can slide this whole curve over, and now our result is right near the middle. That is the idea. This is not a weird result. That's our alternate hypothesis. Let's go with that one instead. If we get a weird result, from assuming, let me write it that way, from assuming H naught is true, then maybe we should reject H naught. Maybe it's not true after all. And that's what we would do in this case. We would reject H naught. Okay, so we've gone through this a long, slow, careful way. From our initial assumption, we assume the null hypothesis is true, and under that assumption, we see if the result that we got winds up being a weird or not weird result. If it's not a weird result, then yeah, maybe this was a totally fine assumption to make. If it's a weird result, then maybe it was a terrible assumption to make, and we should go with the alternate hypothesis instead. That's the gist of the entire problem. The question is, how do we decide if our result is weird or not? We just did the critical value method, where we compare these two z-scores, the z-score that cuts off the region we're going to consider weird versus the z-score of the actual evidence that we got. And we compare those to see if it's weird. If we did the p-value method, which is our second method, so the p-value method, and this is a much more common method, it turns out. This follows the exact same idea and the same exact procedure, except instead of comparing two z-scores, instead of comparing z-scores to decide if our result is weird, we'll just compare the two areas themselves. So going back up to the picture that we did before, The critical value method, we compared these two z-scores. In the p-value method, I'm going to compare these two areas. This little tiny area compared to the one that we've already drawn, I'll do it in blue, this larger area that kind of contains it. So I'll just compare the areas instead of the z-scores of those same regions. And what we get is, again, a picture that looks like this. I can say that this is the z-score that cuts off the region we consider weird, or I could go by the entire area of that whole region. That's alpha. And I could compare, here's our result, some result in here. Here is our, so this is the critical value. This is the significance level. This z-score right here, some z that we get here, some other number, that is our test statistic. And this last little area times that's right here in this region, that area right there is what we call the p-value. So I can either compare this number and this number, the two z-scores, or I can compare this number and this number, the two areas. So this is an area, this is an area, whereas this one is a z-score, and this one is a z-score. We can compare either of those two, and that's the only difference between the critical value method and the p-value method. The p-value method is nice because this area, the p-value actually gives you the probability. So the p-value method is generally preferred. Because the p-value itself, that area, gives the probability of the result that you received. So getting the result that we got, meaning in essence, it gives us the probability of getting the X bar as extreme as the one that we found. So basically, if you think of alpha, the significance level, as being the area we consider weird, so in this case our default we said was like 5%, maybe the result that we got only occurs 1% of the time. So not only do we know that it's weird because it's less than 5%, but I can tell you exactly how weird because it occurs only 1% of the time. We can actually find this area. And so that is going to be the procedure in the p-value method. And I will outline the modifications in just a minute. We will do this example again in a streamlined way. So let me do the same example, but I want to write out our procedure. So let me break all of this down into something that goes a little bit faster. Okay, so we've just spent a ton of time doing this problem, talking about the ideas. Let's boil it down to the procedure the same way that we did with the confidence intervals. We talked about it conceptually for a long time, and then we said, oh, it's really just a 5-step process. This one's really going to be a 6-step process. And so let me write out those steps. Step number 1, we need to state the null and alternate hypothesis. And so it's going to be H naught says that mu is equal to some value mu naught, and the alternate hypothesis can take one of several forms. It could be mu less than mu naught, it could be mu greater than mu naught, or it could be mu simply not equal to mu naught. And these are, again, the way that I've written them. This is the left-tailed, right-tailed, and two-tailed versions of that alternate hypothesis. One of those will be the form that we use. The next step is going to be where we define what we consider weird. And there's two different ways to do that. So if we're doing the p-value method, we want to define weird with an area. So all we have to do is decide what our significance level is. It's given in the problem. It may not be 0.05, it may be 0.01 or 0.1, etc., but it'll be given. It's just an area / probability. And so what we're saying here is we're defining weird as anything that happens less than 5% of the time, or in this case, anything that happens less than 1% of the time, or in this third case, anything that happens less than 10% of the time. We get to pick, or alternatively, it will be stated in the problem. If we're doing the critical value approach, so if we're doing the critical value method, I need to define what weird is, not with an area. So again, this was, how did I do it before? I think blue. This is an area. I will define it with a z-score. And the critical value is either going to be z sub alpha, negative z sub alpha, plus or minus z sub alpha over 2, depending again on whether we are, in this case, switch the order here. This is the right-tailed case, left-tailed, and two-tailed. So it's going to be that value that we find in table A3, and it's a z-score. So we can define what we're going to consider weird either in terms of an area or in terms of a z-score. And again, it will also depend on what the form of our alternate hypothesis was. And so we'll do some examples of all of these down the line. The third step, here's where we actually look at our evidence. So we need to compute the test statistic. We did that earlier. It's the z-score of our evidence. So in this case, it was our particular value of x bar. X bar minus mu naught over sigma over the square root of n. This was the number that gave us the 2.8 earlier. So this is our actual evidence, right? The z-score of the evidence. That's what this is. Step number 4. If we're doing the critical value method, we're good to go. I defined what I'm going to consider weird in terms of a z-score in step 2. We computed the z-score of our actual evidence in step 3. I have the 2 z-scores I need to be able to compare to decide if this result here is weird or not. So at this point, we want to, if we're doing the critical value method, we've got everything we need. I'm going to skip this step entirely. But if we're doing the p-value method, this is the point where I want to convert that z-score. So I want to find the p-value, which is the area to the extreme of the test statistic. So going back up to our picture, again, one of the many pictures, to find this p-value, I just need to find this area. It's the area to the right, in this case, of this particular test statistic. If it was left-tailed, it would be the area to the left. If it was two-tailed, I want to get this area and its mirror image over here. And so we would find both. So that's basically the idea. When I say the word extreme, I say the word extreme because when it's right-tailed, it'll be to the right, but when it's to the left-tailed, it'll be to the left. It just means further into the tail. Find the area further into the tail compared to where the test statistic winds up. So find the area associated with the test statistic. And once we've done that, now I have everything I need for the p-value method. And so step 5 is where we actually do our comparisons. So determine if our result is weird. And by our result, I mean the evidence is weird. How do we do this? Again, if we're doing the critical value method, I need to compare those two z-scores that we found. So our result is weird if the z-score that we found for the test statistic, if z, our test stat, is more extreme, again, using this word extreme again, than the critical value. So if, which is, again, either z sub alpha, negative z sub alpha, or plus or minus z sub alpha over 2, depending on whether we are right-tailed, left-tailed, or two-tailed. So that's why we have, again, the word extreme. In the right tail, we want this z-score to be to the right of this one if it's weird. If it's in the left tail, we want this z-score to be to the left of this one. If it's two-tailed, depending on which tail it falls in, it can either be to the right or the left, depending on whether or not this z-score falls in the right tail or the left tail. But again, we just want to know if this z-score is further into a tail than whatever the cutoff for weird was. So that is our critical value method. And in the p-value method, I'll know if my region's weird. We've already taken into account this idea of extremeness. Our result is weird if the p-value, and I think in the book they use a capital P, possibly, don't really remember, is less than alpha, which is our significance level. So if p is less than alpha, then it's weird. And again, looking at the picture to see why this makes sense, in this picture, our result is in the weird region, right? Here's the big weird region. Our result's within that. So this area definitely is going to be smaller than this larger area if it falls inside. Whereas if this point, if instead of falling here, it had fallen over here, now my p-value would be the area to the right of this region, and I would get a p-value that was larger than the area of this region that we consider weird. So it all depends on where that p-value falls. If this area is smaller, it must be inside of it. It must be in the weird region. If this area is larger than this area, it must have fallen outside here, so it takes up a larger area. So that is the idea there. Long story short, in this step, how do we interpret this? What we do is we reject H0 if our result is weird. Right. The whole reason that we got a weird result is because we assumed that H0 was true. If we're getting a result that's weird, maybe a better explanation is that H0 isn't true and we should reject it. And the absolute last step is state your conclusions. Go back and actually answer the question that was asked. Get done with all the math. State your conclusions in plain English. I want a sentence. And so we'll do an example of this going forward.